Hello, and welcome to my video about the logic of alternate inference chains, or AICs as they're called. In the last video, we learned what constitutes a strong link and what constitutes a weak link, and I hope you all have a good handle on their definitions now, because today I'm going to show you that by stringing strong and weak links together in a certain way, it allows us to draw various conclusions and make deductions about what is true and what is false in a Sudoku puzzle, which will of course help us solve it. AICs are usually considered to be one of the more advanced solving techniques, but I want to at least familiarize you with them here in the early stages. It's not often pointed out, but these alternate inference chains play an important role in many of the simpler techniques, so I think it's a good idea to talk about them right now. In later videos, I will divide these AICs up into several different types, including open-ended chains and various kinds of loops, and I will go into great detail about them with an individual tutorial dedicated to each one. But today, I just want to give you a basic understanding of how they work. We will only talk about open-ended chains today. The loops will come much later in the course. Okay, an inference.
An inference is simply a conclusion reached on the basis of evidence or reasoning. A conclusion reached on the basis of evidence or reasoning. Here's an example. Let's say you just made a peanut butter and jelly sandwich and put it on the kitchen table. And then your phone rang and you went into the next room to answer it and talk for a few minutes. And when you came back to the kitchen, the sandwich was gone and there were breadcrumbs on the floor leading all the way to your dog's bed, and the dog was sitting there with peanut butter and jelly on his nose, licking his lips. At that point, I think you can safely infer that the dog ate your sandwich. That, my friends, is the inference based on the evidence. Ha ha ha. So we will look at the evidence provided by the chains and make inferences based on that evidence, okay? It's really very simple.
In an AIC, by starting with a premise, such as supposing that the first candidate of the chain is false, there is an inference in every segment or link of the chain from one end to the other, based upon the very definitions of strong and weak links that we learned in video number 3. In Sudoku, an alternate inference chain, as its name suggests, alternates between strong and weak links all along the way, and by constructing it like that, it produces a series of inferences.
We will see that if the AIC has an odd number of links, and if it begins and ends with a strong link, in other words, strong, weak, strong, etc., regardless of the length, we will know with absolute certainty that if the first candidate of the chain is false, then the last candidate will be true. And also, if the last candidate of the chain is false, then the first candidate will be true. This ensures that at least one of the endpoint candidates must be true. Let me give you a simple example. Let's say we have a chain of 3 links, one from A to B, and then one from B to C, and then one from C to D. And let's say the first one is a strong link, and the second one is a weak link, and the third one is a strong link. This is the simplest form of an AIC, strong, weak, strong. So by definition of a strong link, if A is false, then B is true. And by definition of a weak link, if B is true, then C is false. And then again, by definition of a strong link, if C is false, then D is true. So, by connecting the logical inferences of these 3 links, we can be sure that if A is false, then D is true, D like in dog, which means there is an implied or effective strong link between A and D by virtue of the chain of inferences. Does everybody get that? And this further means that if D is false, then A is true, because if you run it backwards, the logic is the same because of the strong, weak, strong configuration. You can think of this chain as false, true, or you can also think of it as off, on, off, on. I know this sounds like 4 links, but it's not. there are only 3 links between those 4 positions I just mentioned. You see, there are only 3 hyphens up at the top. Those represent the links. A, B, C, and D are candidates, and the hyphens represent the links between them. 4 stopping points, or candidates, but only 3 links. This is an important point to remember. There is always an even number of stopping points if there is an odd number of links. The number of stopping points equals the number of links plus 1. For example, if there are 5 links, then there has to be 6 stopping points, or candidates. Now, of course, with this so-called effective strong link between the 2 endpoints, the formal definition of a strong link still holds. If A is false, then B is true. But be aware that unlike a strong link in the conventional sense, i.e. between the only 2 remaining same-digit candidates within a house, or between the only 2 remaining candidates in a by-value cell, where one of the 2 candidates must be false, in this case, when we're looking at the 2 endpoints of an AIC, it is actually possible that both endpoint candidates could be true. At least one of them must be true, but they can both be true. That's right, they can both be true. However, there is one obvious exception to this, where the 2 endpoint candidates of the AIC cannot both be true, and that is when we have a chain that begins and ends with the same digit, and those 2 same-digit endpoint candidates lie in the same house and can therefore see each other. In this case, one of them must, of course, be false. It is not possible for both of them to be true if they can see each other. But this situation does not pop up very often. So there is an effective strong link between the 2 endpoints, which means if one is false, then the other is true. But this does not preclude the possibility that they may both be true, unlike a strong link in the conventional sense. Again, if the chain is properly constructed, the logic works both ways, meaning you can start at either end of the chain. But the net result is that if either one of the endpoints is false, then the other endpoint must be true, i.e. an effective strong link. And this ensures that at least one of the endpoint candidates has to be true. And knowing this allows us to eliminate other candidates in the puzzle based upon their positions in relation to the endpoints of the AIC. Like if the AIC begins and ends with candidate 3, for instance, then any other candidate 3 that can see both endpoints must therefore be false and can be immediately eliminated. Let's take a look. Okay, here we have an AIC of 3 links. And we will use the format blue to yellow will be a strong link, and yellow to blue will denote a weak link. And we'll use that system for the rest of the tutorials throughout the course. So in column 3 here, we have a strong link from this top blue 3 to the yellow 3, because they are the only 2 3s in column 3. I mean, there are imagine that there are other candidates in these cells, but I just want to isolate the point of what I'm trying to show you here. So there's a strong link because they're the only 2 3s. And this is a weak link up to this 3 because there are more than just 2 3s in this box, this block. So that's a weak link, which is fine. And then we have only 2 3s in row 4, so that's a strong link. So we have strong, weak, strong. And so now we know that this assures us that one of these endpoint 3s, this blue one and this yellow one of them must be true. So if there is a 3 in the puzzle that can see both of those at the same time, that will be false and you can eliminate it. Now the only place that can occur in this particular puzzle here is in this cell, because there can't be one here, even though that can see both of those 3s. If there was a 3 here, then the first link would not be a strong link. There'd be 3 3s in column 3, so that wouldn't be a strong link. So that can't be there. That's just not there. But there can be one here, and if there's a 3 in this cell, you can eliminate it because it can see this 3 because it's in the same row, and it can see this yellow 3 because it's in the same column. So strong, weak, strong. There's your AIC. There's the endpoints. In this cell, this candidate 3 can see both of those endpoints, therefore it is false and you can eliminate it. Now here's another configuration. Let's start again here, and this is a strong link from this 3 to this 3, and then this is a weak link, and then this is a strong link going across. You know, I wish I could draw on my screen, but I can't, so you're just going to have to follow my mouse. So strong, weak, strong, and then this is a weak link, diagonally down to this blue 3, and then finally a strong link up to this 3. So here are the endpoints. This 3 and this 3 are the endpoints of our AIC. Now which cells can see both of these 3's? In this case, there are six cells that can see both of those 3's. And they lie here. Now this is kind of tricky, but these 3 cells can see this 3 because they're in the same block, and they can see this 3 because they're in the same row. And these 3 cells up here can see this 3 because they're in the same row, and they can see this 3 because they are in the same block. So these are the elimination squares. But however, once again, because we have a strong link here, there's not going to be a 3 there, otherwise that wouldn't be a strong link. There'd be 3 3's in column 3, so that can't be. And here, there can't be a 3 in this cell because this would not be a strong link, and we need that to be strong. Strong, weak, strong, weak, strong. So in this case, the only cells that could have eliminations possible are these 4 cells. And if there was a 3 in any of those 4 cells, you can eliminate them because these 2 3's can see this blue 3 and they can see the yellow 3 because they're in the same block. And these 2 3's can see this blue 3 because they're in the same block, and they can see this yellow 3 because they're in the same row. So all 4 of those 3's in this case, I mean, there may not be any there, but if there's 1 or more, you can eliminate them because they cannot be true because one of these 3's must be true. Is that clear? Good. And all this happens because we alternate the links strong, weak, strong. It's pretty clever.
The chain must have at least 3 links to be an AIC, but after that, there is no limit to the number of links as long as it begins and ends with a strong link, and it must also therefore have an odd number of links. So it can be 5, 7, 9, 11, or 13 links, or as many as you can find and chain together.
I realize all this may sound a bit confusing at first, but let's take a look at a few examples of how certain candidates are proven to be false and can therefore be eliminated, and I'm sure everything will eventually become clear. Once you know what to look for and get the hang of it, it's really a piece of cake and a lot of fun. You'll see. So basically we have 2 types of open-ended AICs. And by open-ended, I simply mean that it is not a loop and that it has 2 separate endpoints. Type 1 would be where the chain begins and ends with the same digit candidate. Like it might begin and end with candidate 3, for instance. And type 2 would be a chain that begins and ends with 2 different digit candidates. Like it might begin with candidate 5 and end with candidate 9. In an AIC type 1 that begins and ends with the same digit candidate, which is by far the most common type, there are 3 ways or configurations in which the endpoints can relate to each other. 1, where the endpoints are not in the same chute. 2, where the endpoints are in the same chute but not in the same house. And 3, where the endpoints are not only in the same chute, but they are also in the same house, which is kind of rare, but definitely possible. So let's take a look at all that. Okay, the whole idea of putting together these AICs is to allow us to eliminate candidates in the puzzle that are proven to be impossibilities. So let's first take a look at chains that begin and end with the same digit candidate. Here we see 2 candidate 3's that are highlighted in gray. Let's imagine that they are the endpoints of an AIC. We don't need to see the chain, but they are the endpoints. So that means that because they are not in the same chute, there are only 2 cells in the whole puzzle that can see both of those cells, and they are here. These 2 red cells, each one of them can see both of the gray 3's, and they're the only 2 cells in the whole puzzle that is true for, that they can see both of them. So this means that because one of these gray 3's has to be true, That means if there is a 3 in either one of these red cells, it is false, and you can eliminate it. And likewise, if we have a chain that begins and ends with these 4s, because they're not in the same chute, there are 2 cells that can see both of those cells. This red cell sees this 4 because it's in the same row, and it sees this 4 because it's in the same column. And this red cell sees this 4 because it's in the same column, and it sees this 4 because it's in the same row. So that means if there is a candidate 4 in either one of these red cells, it can be eliminated from the puzzle as false, because one of the gray 4s must be true. Okay, now if the 2 endpoints of our chain are in the same chute, then there can be 6 cells with possible eliminations, because there are 6 cells that see both of these 7s, and they lie here. These 3 red cells see this 7 because they are in the same block, and they see this 7 because they are in the same row. And likewise, these 3 red cells see this 7 because they are in the same row, and they see this 7 because they are in the same block. So if there is a candidate 7 in any one of these 6 red cells, they are false. Now, most of the time it doesn't occur that there are all 6 of them. There may be 1 or 2 or 3. But any one of these red cells containing a 7 in this case would be false, because one of the gray 7s is true. Likewise, if we have these 2 9s, they are in the same chute, so there is also 6 cells that see both of those 9s. And they are, let's see, they are right here. These 3 red cells can see both 9s, and these 3 red cells can see both 9s. So if there is a candidate 9 in any one of those 6 cells, it can be eliminated as false. And then lastly, there is an odd situation where both endpoints of your AIC can lie in the same house. And believe me, this is possible. This 6 could be connected by a strong link to another 6 in this row outside the block, and this 6 could be connected to a 6 that's either diagonal or off to the left. So this is possible, and when this happens, there can be 7 eliminations, up to 7 eliminations, and those cells are every other cell in that house. If they contain a 6, they can be eliminated as false. They cannot be true, because the 2 gray 6s are the endpoints of our chain, and one of them must be true, which means all the rest of the 6s in that house are false. In an AIC type 2 that ends with 2 different digits, there can be 1 or 2 possible eliminations at most, but only if the 2 endpoint candidates and the cells in which they are contained see each other. If they do not see each other, then your time spent constructing the chain was unfortunately wasted. But this happens. And even if the 2 endpoints do see each other, it is still possible that there may be no eliminations at all, which would also mean that it was an unfruitful construction. But that's Sudoku. Things do not always work out the way we want, just like in real life. And just like in real life, you simply have to keep on trying. Anyway, let me show you how this works. Okay, let's take a look at a real puzzle. What we're looking for is an AIC type 2 that will start and end with 2 different digits that can see each other. So remember, we're going to use blue to yellow to denote a strong link, and yellow to blue will denote a weak link. So let's start on this 3, and we look in row 7, there's only 2 3s, so this is a strong link from this 3 to this 3, because they are the only 2 3s in row 7. Then from this 3 to this 1 is a weak link, because there are 4 candidates in that cell, so between any 2 of them there is a weak link. So that's what we want, strong, weak. Then from the 1 to this 1 is a strong link, because they are the only 2 1s in column 3. So we have strong, weak, strong. Then from this 1 to this 4 is obviously a weak link, because there are 4 candidates in that cell. And from this 4 to this 4 is a strong link, because they are the only 2 candidate 4s in row 8. And now that makes our chain. Strong, weak, strong, weak, strong. 5 links. It begins and ends with a strong link. The 2 ending candidates are different digits, and they can see each other, because they are both in this, they're in the same block and they're in the same column. In any puzzle, every candidate is either true or false. It can only be true or false, and those are the only 2 possibilities for any candidate. So many times what we do is we'll look at the two cases. We'll first assume that a candidate is false and see what the consequences are, and then we'll assume that it's true and we'll see what the consequences are. And if they lead to the same conclusion or the same result, then we know that has to be true, and that's called a verity. V-E-R-I-T-Y. And that is the case when all possible cases lead to the same conclusion. So let's do that right here. If this first 3 in the chain is true, then this 3 here must be false, because there can only be one 3 in column 8. So if this 3 is true, that 3 is false. Now the other case, if the 3 is false, this first 3 is false, we know by the chain there's a strong link, there's an effective strong link between the 3 and the 4, the endpoints. So if the 3 is false, the 4 is true. That's the definition of a strong link. If A is false, B is true. So if the 3 is false, the 4 is true. And if the 4 is true, then there's only 2 candidates in here. That's the answer to this cell, and that can't be a 3. So if the 3 is true, this can't be a 3. And if the 3 is false, this can't be a 3. So we know for a fact that you can eliminate that 3 with certainty. Now what we're going to do is we're going to go backwards, and we're going to do the chain, the same exact chain, but we're going to go backwards. We are going to start on this 4, and there's a strong link here, then a weak link to the 1, a strong link to the 1, a weak link to the 3, and a strong link to the 3. So really it's the same exact chain, except now we're starting on the 4, and I told you you can go either way. It works both ways. So the logic is exactly the same. Then we'll take both cases for this 4, this blue 4 down here. If the blue 4 is true, then this 4 cannot be true, because there can only be one 4 in this column. And if the 4 is false, then the 3 has to be true by virtue of the chain, because if A is false, B is true. So if the 4 is false, then the 3 is true, and if the 3 is true, it has to be the solution for this cell, and the 4 cannot be true. Does everybody get that? So both cases eliminate those unlinked candidates, and then you can, let me get this going here. This is these are the solutions to those cells, so you fill them in. All right, let's look at a different example. All right, let's take a look at example 2 in this particular category. So we're looking at an AIC type 2, which is an alternate inference chain that begins and ends with a strong link, and it begins and ends with 2 different digits. All right, this one is going to be of 7 links. All right, and we're going to use blue to yellow to be strong. So we're going to start on this 7, and from that 7 to the 1 is a strong link. Then there are several 1s in row 1. So from this one to this one is a weak link, which is perfect. That's what we want. So strong, weak. Now this is a bi-value cell. So from the 1 to the 2 is a strong link. Strong, weak, strong. Now we're going to go all the way down to this 2. And this is a weak link because there's an extra 2 in this column. So there's 3 2s in column 2. So from this 2 to this 2 is a weak link. So we have strong, weak. Now there are only 2 2s in row 9, so this is a strong link. And now we're coming across this situation where I said you can use a strong link as a weak link. The 2 is strongly linked to the 1, but in the chain, we only need a weak link. But the strong link has the properties of a weak link, so we can use it as such if you remember from the video on strong links and weak links. So from the 2 to the 1 is what we call a surrogate weak link. It's a strong link, but it can be used as a weak link. And then, lastly, from this 1 to this 1 is a strong link because there are only 2 1s in block 8. So the chain begins on this 7. Now don't confuse it with the 1 because we've got a 1 down here, but it starts with the 7, the blue 7, and it loops down and comes up here and ends on the 1. So here we have the AIC begins with the 7, ends with the 1, and they are in cells that see each other. So there is an effective strong link between the 7 and the 1 because they're connected by the chain. So let's do the same thing we did in the last example, and we'll start by saying if this 7 is true, then this 7 cannot be true because all the other 7s in this column will be false if this 7 is true. So this particular one cannot be true. So if this 7 is true, this 7, let me note it here in red. So that cannot be true. Okay? So if this 7 is true, this is false. Now let's do it again. If this 7 is false, then by virtue of the chain, if the 7 is false, this ending point 1 is true. And if this 1 is true, all the other candidates in that cell are false. So if the 7 is true, this 7 is false. And if the 7 is false, this 7 is false. So this 7 is false no matter what, and we can eliminate it. Now, here we have a bi-value cell on one end, and we have a cell that contains more than 2 candidates on the other end, and this comes up quite a lot. And you'll get AIC type 2s that have multiple candidates in both ends, but most of the time you'll see bi-value cells on one or the other or both ends of the chain. So there you have it. There's the proof again. So we know that now we can eliminate this 1 as being false, and we can eliminate the 7 as being false. So now we can solve this square for 7. Okay, and so what that tells us, like before, let's go back. When you have an AIC type 2, the start digit cannot be true in the end cell, and the end digit cannot be true in the start cell, which means so the 7, which is the starting digit, cannot be true in the end cell, and the 1 cannot be true in the beginning cell. And so that's how you do it. And so you don't have to think of this proof that I just explained every time. All you have to do is remember that when you have the AIC type 2, you can eliminate the start digit from the end cell, and you can eliminate the end digit from the start cell. Okay, let's look at one more example. Okay, here's another AIC type 2 that begins and ends with a bi-value cell, but obviously on different digits. So from blue to yellow will be a strong link. So we're going to start on this 5. From blue to yellow is a strong link, and there's a strong link between that 5 and the 7 because that's a bi-value cell. They're the only 2 candidates remaining in that cell, so that is a strong link. Then the next link only needs to be weak, so from this 7 to this 7 is a weak link because there are many 7s in that block. The next link is from this 7 to this 7, which is a strong link because there are only 2 7s in column 3. Then the next link, all we need is a weak link, but we're going to use this strong link as a weak link. So from this 7 to this 7, it is a strong link, but we're calling it weak. So we have strong, weak, and then to the 4 is a strong link. And from this, I'm sorry, I don't want to go to the 4. From this 7 to this 7 is a strong link because they're the only 2 7s in row 8. And then to the 2 is a weak link. We only need a weak link. It's a strong link. Again, we call this a surrogate weak link. It's a strong link, but we can use it as a weak link, as we know. So we have, starting on the 5, strong, weak, strong, weak, strong, weak. Now up to this 2 is a strong link because there are only 2 2s in column 5. And then the next link only needs to be weak. So from this 2 to this 2 is a weak link. To the 5 is a strong link because it's a bi-value cell. And then across to this 5 is a weak link because there are many 5s in row 4. And that's all we need is a weak link. And then the chain is going to end on this 7, which is a strong link. So the starting point is this blue 5 and the ending point is this yellow 7. Now don't get confused because they're different colors. But you can use, in other words, the first link of the chain can be out of the cell to another cell, if, in other words, to the same candidate, or it can be within the cell. So you can start to a different candidate within the cell. So you can start the chain on any candidate and leave the cell to make the first link, or you can make the first link within the cell, which is what we did. We started for the 5 and we made a link to the 7, and we end on going from the 5 and a link to the 7. So what we have here, another case where we're going to take a look at this starting point 5. Don't forget this was the starting point, and this yellow 7 down here in row 4 is our ending point. So these 2 cells see each other, 7, 5, 7, 5. So if this 5, it's the same logic as we had in the first example. If this 5 is true, then this 5 cannot be true because there can only be one 5 in the column. Okay, and if this 5 is false, then by virtue of the chain and the rules and the definition of a strong link, if 5 is false, then 7 is true. So if the 5 is false, the 7 is true, and if the 7 is true, the 7 is the solution for that cell, and the 5 will be false. So if this 5 is true, this 5 is false, and if this 5 is false, this 5 is false. So that's gone. And doing the other way around, if we look at the 7 here in row 4, if we say if this 7 is true, that can't be true. And if this 7 is false, then we know the 5 is true, because if the 7 is false, the 5 is true. And if the 5 is true, the 7 cannot be true. So this 7 cannot be true whether this is true or false. If this 7 is true or false, it proves that this 7 cannot be. So like I said before, when you have an AIC type 2, you can eliminate the start digit from the end cell and the end digit from the start cell. So the start digit is 5, so you can eliminate that from the end cell, and the end digit is 7, you can eliminate that from the start cell. And then you can solve the 7 and the 5 for those are the solutions to those cells. Okay, before I show you the next example, I want to talk about something that I'm not sure I made 100% clear in the earlier videos. And that is, when you are linking candidates, there are some rules that you have to follow. If you have a same digit candidate, like 2 8s, if you want to connect 2 8s, they have to be in the same house. So these 2 8s are in the same column, which means they're in the same house, and they see each other, and they are connected by a link. And it doesn't matter if it's strong or weak. Right here it's a weak link because there are other 8s in this column, but still you can link those 2 8s. Okay? But you cannot link, say, this 8 with that 8, because they don't see each other. So the only way you can link 2 same digit candidates is if they see each other, which means they have to be in the same house. So, and there can't be 2 candidate 8s in the same cell, so there's no way you're going to connect an 8 to another 8 within a cell. The only way you can connect 2 same digit candidates is in 2 different cells that are in the same house, like that. Okay? So you can connect this 8 to that 8 because they're in the same row, and you can connect this 8 to this 8 because they are in the same block. Okay? But you cannot connect this 8 with that 8, for instance, because they do not share any house in common. Okay? So that's for same digit candidates. For different digit candidates, they must be in the same cell. So, for instance, you can connect this 7 with this 8, and you can connect this 7 with this 3 because they are in the same cell and they're 2 different digits. But you cannot connect this 7 with this 8 because even though they are in the same house and can see each other, they're unrelated. The only way there can be a link between 2 different digits is if they are within the same cell. So there's a link between this 7 and this 8, but there's no link between this 7 and that 8. And there's a link between this 7 and this 3, but there is no link between this 7 and this 3, even though they are in the same house. You cannot link 2 different digit candidates unless they lie in the same cell. Okay, I hope that's clear. Okay, here's an example of an AIC type 2 that does not have a by-value cell on either end. All right, so we're going to start on this one, and I believe there are 13 links in this chain, if I'm not mistaken. Here we go. I'm going to start from this one to this one is a strong link, because they're the only 2 1s in that column. And this is a weak link, a strong link, by-value cell. From this 5 down to this 5 is a weak link, then to the 9 is a strong link. Then from this 9 to this 9 is a weak link. From this 9 to this 9 is a strong link. And then this 9 up to here is a weak link. And then there are only 2 9s in this row, so that's a strong link. And then we're going to weakly go to the 2, and then it's a strong link to this 2, because they're the only 2 2s in that column. And then this is a weak link here. And then lastly, the strong link, we're going to end on this 2 to this 2 is the strong link. So we begin on this blue 1 and end on the yellow 2, and notice that these are not by-value cells. Here, let me mark them for you so you can see. These are the 2 target cells. So the beginning digit is here, this 1, and the ending digit is the yellow 2.
this 1, and this 2. So now we use the logic that we always use, and we're going to consider the two cases if this 1 is true or false. So if this 1 is true, then all the other ones in this row will be false, which means we're only looking at these two cells. You can't just eliminate because you don't know, or this is only an assumption. It's a premise. If this 1 is true, then we know this 1 in our target cell is false, because we don't know if that's true or false, the first one. So we can't do anything with this 1 over here. That's out of the picture. So if this first 1 is true, this 1 is false. Let me make it red for you. So this 1 is false. And is that red or green? I'm colorblind, so I guess that's red now. So, okay, so if this 1 is true, that is false, and you can eliminate it. All right, and if the 1 is false, then by virtue of the chain, the 2 is true. And if the 2 is true, all the other candidates in that cell are false. So that 1 is false either way. So regardless of whether this first 1, the beginning 1, is true or false, this 1 cannot be true, and you can eliminate it. Now we'll go the other way on this yellow 2 over here. If this 2 is true, case 1, then this true has to be false. And remember, you can't do anything with this 2 here in this cell because it's not in the chain. So if this yellow 2 is true, then this 2 is false, and you can eliminate it. Now, in the other scenario, is if this 2 is false, then by virtue of the chain, the 1 is true. Okay, because that's the other endpoint of the chain. So if the 2 is false, the 1 is true, and if the 1 is true, then this 2 is false. So the 2 is false either way, whether the 2 is true or false, this 1 is false both ways, so you can eliminate it. And so again, you can eliminate the start digit from the end cell, which is a 1, so you can eliminate that, and you can eliminate the end digit, which is 2, from the start cell. So there are your two eliminations. You start with a 1 and end on 2, so you can eliminate the 2 from here, and you can eliminate the 1 from there. Okay? Okay, before we wrap up today, I'd like to make a couple of other points, real quick. And that is, when you're making chains and loops, you can only use any one particular candidate once, and you can't come back and string the chain through it 2 or 3 times. You can either use it once as you're going along, or you can return to it if that's where you end. Like in a loop, sometimes you can return to the same cell or to the same candidate that you start on, and that's okay. But you can't, like for instance with these 6s here, you can't go for a strong link here, and then a weak link here, and then a strong link here, and then a weak link here, and then you can't keep going with, you can't do that. So in other words, you will have used that first 6 twice, and you can't do that. Now if it's a loop, and you start here and end here, that's okay. But you can't just go through it 2 or 3 times and come back, okay? So that's the first rule. You can only use a candidate once in a chain, and you can return to it if it's a loop. Now, in this other example that we looked at earlier, where the start digit here was 5 and the end digit was 7, remember, strong, weak, strong, weak, strong, weak, strong, weak, strong, weak, strong. So we started on the 5 and we ended on the 7. But this other 5 and this other 7, they get eliminated, and they're actually part of the chain. As you saw, they were lit up. You see? So even though they're part of the chain, they can be eliminated. This principle is called cannibalism. So in other words, it eats itself. The chain eats itself because you eat it there and you eat it there. But that's allowable and permissible as long as the rules apply. Now on a side note, in an AIC type 1 that begins and ends with the same digit candidate, if every stopping point, meaning every chain candidate along the way, is also the same digit, like all 6s or all 9s, this is called an X chain, and there will be a separate tutorial dedicated to them. I'll teach you how to construct all the chains in future lessons. But for now, all you need to know is what they look like and the reasons why we can eliminate candidates because of their implications. Okay? Now don't forget, in the adjunct to this video, video number 4A, I will show you several additional examples of all the different types of AICs we have discussed here today. So please make sure to take a look at that when you get a chance.
You should know that when you look at other websites or read books about Sudoku, you will come across various methods of notation for links, chains, and loops. This is so the chains can be written out and described in text. But there are so many variations on this, and they are all so difficult to read and decipher that I have decided not to use them in my course. Instead, I will always try to make everything clear graphically, which will save you the trouble of learning all the different methods of notation. If you want to learn them on your own, that's up to you. But I'm not going to use them here, okay? And I think we'll be just fine without them. Okay, that's it for this lesson. You need to have a solid grasp of how these AICs work, because we will see them pop up over and over again in various forms in many of the techniques that we will cover and learn. And understanding AICs will help you learn any technique that incorporates the use of them much more quickly. So make sure you understand today's lesson fully before moving on to the next video in the series, okay? As always, thanks for watching, and I'll see you in video number 5 on singles, where we will begin the actual solving techniques. Until then, be well and be happy.